All right, so what we're going to do today is we are going to prove the central limit theorem in the case of a Poisson random variable. Why? It's essentially the same proof as we're going to see later. I like the idea of doing a special case first and really building our intuition and just seeing it when the calculation is a little bit simplified. For those of you who are paying attention, you will have essentially a very similar problem to this on the final exam, except rather than doing a Poisson random variable, I will make up some random variable and give that to you. I do not want you to reproduce the general proof. I want you to see it in a special case. So let's start off with Poisson random variables. All right, so we say x is Poisson with parameter lambda. This means the probability x equals n is lambda to the n, e to the minus lambda over n factorial. N is in 0, 1, 2, and lambda is greater than 0. We calculated the moment generating function of x last time. If memory serves, it was e to the lambda, I think e to the t minus 1. Is that what we got last time? And so we know that this is equal to 1 plus the mean times t plus the second uncentered moment over 2 factorial t squared plus dot, 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 dot. So we can now calculate the mean and the second moment just by taking derivatives. The mean is we take the first derivative at 0, that's the mean. We take the second derivative at 0, and that'll be the second moment. And then the variance is just mu2 prime minus mu squared. What's the only concern about taking the derivative here? Is this a function you're jumping for joy to take derivatives of? It's not horrible, but you've got a chain rule. When you take the derivative once, you're going to have an e to the t minus 1 coming down. Then you're going to have to do a product rule with a chain rule. It's not horrible. I wish they gave this problem in Calc 1 so I could then refer back to it now. You have all the cookbook functions they give you that nobody cares about and ask you to take derivatives of. Here is a cookbook function that matters. The exponential of the exponential actually has importance. There is another way to do this, and this is related to some things you may have seen in Calc 3 in terms of calculating Taylor series. So there's a trick for calculating Taylor series. So here's the Taylor trick. The sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus yada, yada, yada. Okay? Let's say I want you to calculate the sine of x plus y. So in multivariable calculus, you would now be taking partials with respect to x and then y, then mixed partials and all those expansions. Or you could just say, screw that, it's a technical term, let u equal x plus y, and expand it out in terms of u, and then simplify. Then you would get x plus y cubed over 3 factorial, oh, that should be minus, plus. And if you only wanted a second order Taylor series, if you only wanted things up to x squared, xy, y squared, you would just stop here. If instead you wanted x squared y, you would take u equals x squared y, and you just go like that. Things become a little bit harder now. If you want a second order Taylor series, this term contributes to the first order and the second order. The terms here, they're no longer all degree 3. What are the degrees of these terms? Yeah, they can go all the way up to degree 6. So if you wanted a fourth order Taylor series, it's now a little bit annoying. You would have to go up to the fourth term here, and you'd have some contributions from this term too. But it's not that bad. You can expand out these polynomials. This is a wonderful way to calculate things. We can do something very similar here. So let me just do the calculation here. So note, e to the t minus 1, it's 1 plus t squared over 2 plus dot, 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 minus 1. So e to the t minus 1 is t plus t squared over 2 plus dot dot dot, or e to the t minus 1 is t 1 plus 1/2 t plus dot dot dot. If I want to calculate e to the t minus 1 squared, this would be t squared 1 plus 1/2 t plus dot 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 squared. In this squared part over here, 1 times 1 is 1. Now the next term, I'm going to have the 1 times the half t, but I'm going to get it twice. What size is that term going to be? T. So this would actually be t squared plus t cubed plus dot dot dot. So if I only needed things to size t squared, I could stop. So we can use this to calculate the Taylor series very easily. So if I have e to the lambda e to the t minus 1, this is 1 plus lambda e to the t minus 1 plus lambda squared e to the t minus 1 over 2 plus dot dot dot. What can you say about the next term? What size in t is it going to be? I'll have a e to the t minus 1 cubed. So what size in t will be the next term? It'll be t to what power?
6.
Not 6. E to the t minus 1 is t, then 1 plus higher order t. E to the t minus 1 squared is t squared 1 plus. So this will be t cubed. If I only care about the first two terms, if I want to calculate the first two moments, all I have to do is get the t and the t squared term. Do I need to worry about the next term over here? No. I can stop. So I get, this is just going to be 1 plus lambda. Now e to the t minus 1 is going to be t plus t squared over 2 plus dot dot dot. The next term is lambda squared over 2. And what's the only term I need to keep from the e to the t minus 1 squared? I just have to keep the t squared term. So if I look at that, I can now just simplify the algebra a little bit, and we'll get e to the lambda e to the t minus 1 is equal to 1. The only t term is coming from here, so I get lambda t. And now if I look at the t squared, I get a lambda over 2 and a lambda squared over 2. So I get lambda plus lambda squared over 2 t squared. I don't have to take any derivatives. If you don't want to do this, by all means take derivatives. But I want to give you a sense of how knowing these expansions can be used to simplify your algebra. And we're going to use stuff like this later. So this is a great way to segue into that. So this implies that the mean is equal to, so what does the mean have to be? Has to be lambda. And the second uncentered moment has to be lambda plus lambda squared. And so the variance is the second moment, uncentered, minus the square of the mean. So we get lambda plus lambda squared minus lambda squared, and we get just lambda. So we now have the mean and the variance of a Poisson. They're both lambda. To me this is annoying, because normally you want them to have different units. Does lambda have any units? No. Lambda is unitless. So that's why it's okay that both the mean and the variance are both lambda, because lambda is a unitless quantity. So it's okay as lambda is unitless. So this, yes?
Where did you get the second moment from?
So I got that from our expansion. Is the moment generating function is 1 plus mu t plus mu 2 prime over 2 factorial t squared plus mu 3 prime over 3 factorial t cubed. So whatever the coefficient of t squared is, that divided over 2 factorial, that's going to be the second moment. So when we expand everything out in terms of t, what we see is here's the mean, and then whatever the coefficient of t squared over 2 is, that's got to be the second moment. And so when we collect the stuff, we see that it has to be lambda plus lambda squared. We don't need any of the other powers of t. That's the advantage of this calculation, is we only need to keep track of things up to t squared, the highest stuff we can drop. We're going to be doing the exact same thing now as we start analyzing the proof of the central limit theorem. But I just wanted to record what its mean and variance are. Any other questions on this calculation? We could have, of course, done this directly, and I think we did this with differentiating identity, weeks ago. So we have lots of ways of calculating. All right. I'm going to try to leave this stuff up on the board because this is going to be useful. We'll write over here, the mean is lambda, and the variance is lambda squared. I do not believe we've calculated this yet. If x is normal 0, 1. Yes, question?
The variance is just lambda.
The variance is just lambda, thank you. It's just a force of habit. I just instinctively want to square it. I apologize. Please keep watching me today. I will almost surely try to square it again. What should we choose lambda to be? I'm sorry? What should we choose lambda to be so that I don't have to worry about being careful? 1. If we choose lambda to be 1, I don't have to worry about squaring it. But we should do the general proof. I don't think we've done this calculation yet, that if I have a standard normal, the moment generating function of the standard normal is e to the t squared over 2. Have we done this calculation yet? Okay, let's do this calculation. We have almost done this already when we've been doing the normalization constant of the normal. So now we're going to start calculating moment generating functions. We've already done a few of them. So let's calculate. So x is going to be normal 0, 1. So its density is 1 over square root of 2 pi e to the negative x squared over 2. Bless you. We've calculated the normalization constant 2 different ways. We calculated by doing the polar trick. We also talked about how you could convert this to a gamma factor. It's gamma of 1/2, maybe with a factor of 2. So we know that this integrates to 1. Let's calculate the moment generating function. All of these proofs start the same way. Every proof involving the moment generating function goes back to the definition of the moment generating function. What's the definition of the moment generating function? Expected value of what? E to the tx, which is the integral from minus infinity to infinity of e to the tx fx of x dx. When you first see this, you should be a little bit afraid. Because either, depending on whether or not t is positive or negative, when x goes to infinity with the same sign as t, this is going to be exponentially growing. You should be very scared about integrating anything that's exponentially growing. Why is it okay in our case here?
The normal decay.
Yeah, the normal decay is faster than exponential. It has an e to the negative x squared over 2. So the decay is so rapid that it doesn't matter what value of t we put in, this is going to converge. So if we try to do the integral, we have the integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2 e to the tx dx. So I'm trying to write this in a certain way to try to highlight what we should do next. Any thoughts on what we should do? Yeah, complete the square. Somewhere between 7th grade plus or minus 2 grades, depending on how you were learning math, you saw the quadratic formula. And one of the big ideas in proving the quadratic formula was this idea of completing the square. It's one of the most powerful techniques we have in mathematics. It's going to allow us to do a really good change of variable. So we want to complete the square here. So this is 1 over square root of 2 pi, integral from minus infinity to infinity, e to the negative 1/2 x squared minus 2tx. The minus and the minus becomes a plus, the 2's cancel. So if I'm going to complete the square, what do I want to put next? Plus t squared. Am I allowed to just add t squared? I have to subtract a t squared. So we get to do some of my favorite things in mathematics. We get to do nothing. But we do nothing in a good way. We've added 0 so that now we have a square. All right, well, now we can pull out the negative 1/2 times negative t squared, because this has no x dependence. So we pull that out, and we get e to the t squared over 2. And now we have an integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x minus t squared over 2 dx. What does this integral equal? 1. Why does this integral equal 1? Yeah, so you could do a change of variables. You could let u equal x minus t, or you could notice that this is a normal. What's the mean of this normal? T. What's the variance of this normal? 1. Very hard to have mean 0, variance 0. We know what this integral is. It's just 1. So we then get, it's just e to the t squared over 2, because this is just 1. And that's the claim. So we claimed that the moment generating function of the standard normal is e to the t squared over 2. So that's our next fact over here. Not surprisingly, this is the most important moment generating function in the course. Why? Well, we're trying to show everything converges to the normal. The way we're going to show things converge to the normal is we're going to show their moment generating functions converge to the moment generating functions of the normal. And then the hope is that if the moment generating functions converge, the densities converge. This is where what class comes into play. No, real analysis is not strong enough for this. Real analysis is weak. Complex analysis. Okay? Any Seinfeld fans here? Okay, the Ukraine is weak episode, if you've seen that. All right. Real analysis is not strong enough to prove the results we need here. We really need bigger results. All right, so what we want to do now is the goal is we're going to let Zn be x1 plus xn minus n times the mean divided by sigma square root of n. The expected value of Zn is what? What's the expected value of Zn? 0. We've subtracted off. Each one of these has mean mu. And what should the variance? The variance will be 1. So here, all the xi's are independent, identically distributed random variables, mean mu, variance sigma squared. A common setup. This is the standardization. And we're going to have z be normal 0, 1. Each xi is going to have some common distribution x. And the goal is to show that the moment generating function of Zn of t goes, as n goes to infinity, to the moment generating function of z of t. And if the moment generating functions converge, then the hope is that the original densities must converge, that the density of Zn converges to the density of z. In a first course in probability, without any prerequisites, no way we're going to be able to get to that. But we can get close, and we can reduce it to some reasonable results. And if you want to see more details, you can watch the complex lectures. I would suggest having like a football game or something on in the background at the same time, and just get some rough flavor. You can read the advanced chapters in the book. But I want to try to reduce the central limit theorem to some reasonable results from complex analysis. That if we can understand how the moment generating functions converge, we should be able to understand how the densities converge. That there should be a nice way to go from one to the other. Now, of course, one of the problems is the moment generating functions don't always exist. So what we often do in complex analysis or in probability theory is it's better to work with something that exists than something that does not exist. And so all you do is you change the moment generating function by replacing, oh, we haven't written it here. So the moment generating function x of t is the expected value of e to the tx. We look at the characteristic function of x of t. It's the moment generating function at I times t, where I is the square root of -1. And it turns out when you put that in, you will have something that's always integrable, that always exists. And the analysis becomes a lot easier because you're actually working with an object. Okay. Rather than proving the central limit theorem initially in great generality, let's do it in the special case of sums of Poissons. So CLT for Poissons. So each xi is Poisson with a parameter lambda, and they're independent. So when we now look at Zn, this is going to be the sum of the x's minus n times the mean over sigma square root of n. This is all in the book. So if you want to just pay attention, I'm not really writing that much that's not in the book. We have two ways to proceed. We could put in the specific values for mu and sigma, because we know what they are, or we could just leave them for now and then substitute later. I would prefer to leave them as they are now, and only when we absolutely must put in their values. The reason is, the more general we make the calculation, the longer we can use this. Okay? So let's start looking at the moment generating function of Zn of t. And then it's not going to be hard to modify what we do for the general case. Well, this is going to be the moment generating function of x1 plus xn over sigma root n minus mu square root of n over sigma of t. And I'm just doing the division over here. In an ideal world as a lecturer, we would have had maybe a 2 or 3 hour marathon class and not had this break called Thursday. But if you go back, remember we proved a couple of results at the end of class on Monday about moment generating functions of sums and the moment generating function of alpha x plus beta. So now we use that. Here's my beta. Beta is negative mu root n over sigma. My alpha is 1 over sigma square root of n. So use the moment generating function of alpha x plus beta of t is e to the beta t moment generating function of x at alpha of t. And what we get is, this is going to be the moment generating function of x1 plus xn. What's my alpha? 1 over sigma root n, so I have t over sigma root n. Oh, and I forgot the beta term. And we have a e, and what's my beta? Negative mu square root of n t over sigma. Okay. So we've used our first, or one of our 3 facts from Monday. Or Wednesday, I guess Wednesday. What's the next fact we're going to want to use? What comes next? I'm sorry? Okay, what about the convolution? So we turn this into product. The moment generating function of a sum is the product of the moment generating functions if they're independent. This is why we love the moment generating function. Most people do not enjoy doing convolution integrals. Okay? You don't really see it televised that often. You don't really have competitions in who can convolve the fastest. Nobody wants to do this. Regular multiplication we don't mind. The whole point of these generating functions is they convert convolution to regular multiplication. So now we use the moment generating function of a product, of a sum, is the product of the moment generating functions. So now what we get is mZn of t is e to the negative mu square root of n t over sigma. Now we have the product, k goes from 1 to n, of the moment generating function of xk evaluated at t over sigma root n. But all of these are the same. So this becomes e to the negative mu square root of n t over sigma. And then just the moment generating function, we'll call that x, of t over sigma root n to the nth power. Okay. Now again, we should be thinking we are really looking at the Poisson random variable. But so far, everything we've done holds in great generality. As n gets really, really large for a fixed value of t, where are we evaluating the moment generating function? 0. If you had to choose a point to evaluate the moment generating function, 0 is a wonderful choice. Right? What is the moment generating function at 0? 1. Great place to evaluate the moment generating function. This is almost 1. That's lovely. Unfortunately, we're raising almost 1 to a huge power. If you look at 1 plus x over n, approximately what is this for any fixed x as n goes to infinity? 1. But if we raise this to the nth power, what does that go to? Not e. E to the x. I put an x over here. So you can have something that's almost 1, but if you raise it to an enormous power, it can accumulate. The danger is this can accumulate because it's not quite at 1. It's a little bit away. It's t over sigma root n. So we're going to need to figure out how much it accumulates. Okay. So we started off by using the definition of the moment generating function. We got to this lovely expression. What should we do now? We could, but I want to avoid subbing in what we know as long as possible. There's something else we can do. Anybody who's, I'm sorry? We don't want to do a substitution. This is a class taught by Professor Miller. Whenever I ask you what should we do, you should always answer, not add 1. I'm sorry, what? Take the log. Why are we taking a log? We have a product, okay? Whenever you have a product, what should you be thinking? I feel like a failure as a teacher. Take, product implies log. Okay? Is this a product? Hell yes. It's a huge product. We have a big factor of n. You have lots of products. Remember when we did the coin toss and we did Stirling's to see the central limit theorem? And we saw that if we just naively combined the exponentials, we actually got the wrong answer because of bad accumulation. But if we took logarithms and Taylor expanded and were careful with the bookkeeping, everything worked out. Whenever you see a product, you should be thinking logarithms, unless you are volunteering in like an elementary school. Okay? And if you're trying to teach 2 little kids, so how do you multiply 4 times 5? Okay, that's probably the one exception. Okay? Otherwise, please consider a logarithm. At the end of the day, if you take a logarithm, what will you probably have to do at the end of the day? I'm sorry? Exponentiate. You have to return to where you started. So you do a logarithm, do the analysis, and then exponentiate. The reason this works so nicely is logarithm and exponentials, they're really nice inverse operations. We want something similar with the density and the moment generating function. That if the generating functions are converging, the densities are converging. We want a result like that. If the logarithms converge, then the exponentials converge. We have a result like that. So you should always be thinking, taking a log. So we take the log and we get the log of mzn of t is going to be, oh, isn't this nice? The log of a product is the sum of the logs. We have an exponential here. When you take the log of an exponential, you get a negative mu square root of n t over sigma plus n times the log of the moment generating function of t over sigma square root of n. All right. At this point, let's save this. All right? So we will save this result. In general, we would now have to expand the log of the moment generating function. Well, the moment generating function is approximately what? Because of where we're evaluating it, the moment generating function is approximately 1. So we're expanding the log around 1. So you should be thinking, the log of 1 plus u is u minus u squared over 2 plus u cubed over 3 minus yada, yada, yada. So we'll be able to use an expansion like that. But I've told you that we're going to look at the Poisson distribution first. There must be a reason I'm so happy and excited about the Poisson. If you look at the Poisson, what do you see? I'm sorry? So, when you look at the moment generating function of the Poisson, what would you love to do to a moment generating function that can be written of the form e to the? Take the log. This one is screaming, please use me as your prototypical example for teaching. Right? It's trivial to take the log of the moment generating function of the Poisson. If I give you almost any other distribution, it's going to be a pain. But it's written as the exponential of a nice function. Right? That's why the algebra is going to be much easier in this case than any other case. So now we use the fact that we have a Poisson. Okay. Now use Poisson. So we have n times the log of mx of t over sigma root n. This is no longer going to hold in general. It only holds for what we're looking at. Is going to be lambda e to the t over sigma root n minus 1. Okay. Fortunately, earlier in class, we talked about how to expand something like this. Oh, yes, I needed n. Thank you. The n from that n. We talked about how to expand this. The minus 1 kills out the leading term, and now we start expanding it. It's actually going to be a lot easier here, because we're not taking the exponential of this anymore. Life is really good. So we get n lambda, and then e to the t log n is just 1 plus t over sigma root n plus t squared over sigma squared n with a 2 plus t cubed over 6 sigma cubed n to the 3 halves plus dot 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 minus 1. Okay. So the main term, the 1's cancel, and we're going to get n over square root of n is square root of n lambda over sigma t. Now let's look at the t squared term. We're going to get the n's cancel perfectly, lambda over 2 sigma squared t squared. Now the next term, we really care about how things depend with n, right? What's the size of this next term when we multiply by n? 1 over square root of n. So we write, I'll write some e for error of size 1 over square root of n. And if you just keep marching down the line, you'll keep getting more and more powers of n. You'll keep gaining an extra square root of n. Things are going to converge rapidly. It's dominated by a geometric series. You're going to have an error of size 1 over square root of n. As n goes to infinity, is this going to matter? No. So now we substitute. And now we get the log of mzn of t. We have the negative mu square root of nt over sigma. What's mu? Lambda. What's sigma? Square root of lambda. So we get lambda square root of nt over square root of lambda. from the first piece over here, from this piece over here. And now we substitute in for this part. All right, so now for the next part, we have plus square root of n lambda over sigma, which is square root of lambda t, plus lambda over 2. And what's sigma squared? Lambda. I'm not going to do the lambda squared. I've already made that error once today, only making it once. T squared plus some error of size 1 over square root of n. And I dropped the minus sign, so let's put the minus sign in. What do you notice from the first two terms? They cancel. And then this term over here, lambda over lambda, so we get the log of the moment generating function of Zn of t is equal to 1/2 t squared plus an error of size 1 over square root of n. Now what do? Raise it to e. And so when you exponentiate, you get the moment generating function of Zn of t is e to the t squared over 2 times an exponential of an error of size square root of n. So I will write that up here again. Okay, so we get the moment generating function of t is equal to e to the t squared over 2 e to some error of size 1 over square root of n. Well, what is this over here? What does that equal? The moment generating function of the standard normal, the moment generating function of what I want, and here I have the exponential of something of size 1 over root n. As n gets very, very large, this is the exponential of 0. What's the exponential of 0? 1. So we get that mzn of t converges to mz of t as n goes to infinity. And we even have some control over the rate of convergence. So all we now need is just a general result that says if the moment generating functions converge, the densities converge. Okay. Any questions about this argument? As we have this on the board, I'd like to now do the general case right now because we've basically got all the tools here. The argument for the general case is the same up to here. The only place where it now changes is we no longer have a nice formula for the log of the moment generating function. So we're going to have to do more work for that. But everything else is the same up to here. This is the advantage of doing the general calculation. So now we'll handle the general case. So general case. So start at the save point. Right, let's do it. N log moment generating function x of t, not of t, of t over sigma square root of n. This is going to be n, the log, and I'm going to substitute in what the moment generating function is with its Taylor expansion. It's going to be 1 plus mu t over sigma root n plus the second moment t squared over 2 sigma squared n. I'm squaring this so I get t squared over sigma squared n. I have a factor of 1/2. The next term is going to be of size t over sigma root n cubed. When I cube that, what's the size going to be as a function of n? 1 over n to the 3/2 plus some error of size n to the 3/2. And you can keep going. I'm going to be a little bit cavalier in the bookkeeping in terms of what all the other stuff is. You need some control over the convergence rate to handle things, but if the moment generating function converges, and so the assumption is always the moment generating function converges in some interval about t equals 0, then you can sum the tail. And the tail will be dominated by the first term you keep. So this is by assumption that moment generating function converges for the absolute value of t less than some delta greater than 0. At some point, we should use the fact that the moment generating function exists and converges. This is one of the places where we use it. So we can basically just amalgamate all those errors together. Now we want to expand and use the log of 1 plus u is u minus u squared over 2 plus u cubed over 3 minus dot dot dot. Well, actually, we can just leave it as plus some error of size u. Because u is going to be much less than 1, the error term in the log expansion, we can just use the geometric series and bound that by some error of size u cubed. When you look at this, the log of this quantity, so this whole mess here, this is going to be our u. You might want to say that we only have to keep the first term, because the second term is much smaller than the first term. We shouldn't need to keep it at all. Why are we going to need to keep the second term as well? What's the danger? There's an n out front. This n takes anything that's small and magnifies it enormously. So something of size 1 over square root of n, when you multiply by n, you're going to get something going off to infinity. That's bad, but we have a negative mu root nt over sigma, which will perfectly balance this out, because that'll be a positive mu square root of nt over sigma. Perfectly balance out. When the n hits this piece, the n divided by n is size 1. This piece will exist. When we square things for the u squared piece, when this hits itself, it's going to give us a 1 over n. When you multiply by n, this will contribute. When you have for the cross term for the u squared, when this hits this, that's going to give us an n to the 3 halves in the denominator. When you multiply by n, will it matter? No. When this hits itself, you'll get a 1 over n squared. When you multiply by n, will it matter? When anything hits this, will it? No. So the only things that will matter is for the u term, both of these matter. For the u squared term, only this matters. All right, so doing the analysis, we now get n. So the u term, we're going to get mu t over sigma root n plus mu 2 prime t squared over 2 sigma squared n. I'm going to just put all the error terms at the very end. Now we have minus the u squared over 2. The only thing that matters is the square of this. So minus mu squared t squared over 2 sigma squared n plus some error of size 1 over n to the 3 halves. Okay? Let's keep doing the algebra. When we multiply through, we're going to get a mu square root of n t over sigma. Now for the next one, the n's cancel. We get mu 2 prime minus mu squared over sigma squared t squared over 2 plus some error of size 1 over square root of n. Anybody recognize mu 2 prime minus mu squared? This is sigma squared. Sigma squared over sigma squared is 1. So we get that this is just mu root n t over sigma plus t squared over 2 plus some error of size 1 over square root of n. We can now feed that into what we had over here. And so when we try to feed that in over here, we have the mu square root of nt over sigma with a minus sign. That's going to cancel our first term. And then we're just left with a second. So, okay. So we get the log of mzn of t. The main terms cancel, which is really good because the main terms blow up. We don't want any of those to survive. and then we're left with just the error with the next term. So we get t squared over 2 plus error 1 over square root of n. Boy, this looks similar. This is what we had a moment ago. We exponentiate, and we get mzn of t is e to the t squared over 2, e to the error of size 1 over square root of n. Hasn't changed in the last 10 minutes. Actually, it's been more like 5 minutes. What is e to the t squared over 2? Normal. Moment generating function of the normal. So mzn of t is mzt, and then an error of size 1 over square root of n. Therefore, the moment generating function of zn of t, as n goes to infinity, goes to the moment generating function of the normal. And now we need those results from complex analysis that say this implies the densities converge. Was there a question? No. Yes?
So the reason we're centering the ZN is just to make the algebra clear?
It's more than just to make the algebra clear. It's so that we're always converging to the same normal.
If we didn't center it, we could just
It would converge to a different normal. And we want to make sure that it's converging to something that is well behaved as n goes to infinity. We don't want the mean to be growing because then we'd constantly be changing. We want to be converging to one fixed distribution. So we're converging to the standard normal because of this folding. This is truly remarkable. It is not depending on the shape of the distribution. As long as your density is nice, if you keep taking sums of independent copies, it's going to become normally distributed when you look at the standardization. This should be surprising. Why does the shape of the distribution not matter? Shouldn't uniforms and exponentials have different behavior? Where does the shape of the distribution come into play in these calculations? So, yes?
The moment generating.
Where in the moment generating function?
When taking all the moments.
Right, so at what point do we start to see the shape? At what moment?
First moment.
I'm sorry? No, because if I have a nice probability distribution, I can always adjust to have mean 0. I won't do this on the next exam, I promise, but I can always adjust to have mean 0. I can always adjust to have variance 1 if my variance is finite. I can always rescale. I can change units. What's the first moment of your distribution that really conveys shape? The skewness, the third moment. It's at the third moment that you start to see the shape. So when we start looking at what's going on, it's not until the third moment that we see the shape of the distribution come into play. Well, if you look at our analysis, the third moment does not come into play in the limit. Where does the third moment live? It lives in this error term. It affects the rate of convergence to the normal. So not surprisingly, a uniform distribution and an exponential distribution may converge at different rates to normality. The uniform distribution is symmetric about the mean, the exponential is not. And so the fact that the third moment of the exponential is non-zero could impact the rate of convergence. But this is the miracle of the central limit theorem, that the higher moments, the shape of the distribution only affects the rate. So on the exam, you will not be able to mimic the general calculation and then at the end of the day plug in sigma and mu. I will give you a probability distribution. I'll say, just basically mimic what we did for the Poisson, and you can start off at the save and just work with that. Right? This is essentially it for the new material for the semester in terms of testable stuff. We're now going to start going into applications and how you use this, but central limit theorem in a day. All right. Have a good weekend.